welcome back. We're going to take a look in this video some properties of the dot product and how we use them to define a general version of a dot product for various vector spaces. So to start, I want to point out theorem 5.3 here, which has all of our very important properties for the dot product. So 1, we have our commutativity. 2, we have our distributivity, which makes sense. We should be able to sort of factor in, distribute a product. And then 3, we should be able to, again, distribute a scalar into a product, right? If you were taking like 2 times 5 times 6 as real numbers, this would be the same thing as 2 times 5 times 6, or 5 times 2 times 6. That's all this is saying. Right? 4 we'll get back to. 4 is actually not one of our foundational properties, but it is a useful one, the fact that the dot product corresponds to a length. Right? So we're going to kind of, let's lightly cross out 4 here. Right, and then 5 says that the dot product is always at least 0 if you're taking the dot product of something with itself. And you only get 0 if you started with the 0 vector. So this kind of goes back to our length thing, that the length of something is always non-negative, and you only have 0 length if you have the 0 vector. Right. So with these 4 properties alone, 1, 2, 3, and 5, we have some awesome theorems. We have the Cauchy-Schwarz inequality, which says that relates a dot product with some lengths. The triangle inequality, which tells us that the length between 2 points, the shortest distance is the straight line rather than taking the alternate route. Alright, and then the Pythagorean theorem, which we all know, that says that if we have a right angle between our vectors, then the length of those 2 vectors, each individually squared, is the square of the length of the hypotenuse. So these are all properties of the dot product that fall out of these original starting 4. Right? So what we're going to do is we're going to define an inner product to be something that has these 4 very important properties: the commutativity, the distributivity. Right? Again, this should look like distributing the u to the v and the w. Right? And then the fact that we can stick the c in, and here again we want to make sure our products are positive, or at least non-negative. And again, out of these 4 general vector spaces, we get the Cauchy-Schwarz inequality, the triangle inequality, and the Pythagorean theorem still. Right? So all we need are these 4 properties. We don't actually need to know what the inner product is. Like here, we could have proven these without actually using the definition. I'm pointing at my screen, but we could have proven all 3 of these without actually using the definition of the dot product, which is super awesome and really is what should lead us to want to generalize this to a general vector space. All right. So what are some examples of inner products? So one example is certainly the dot product on r to the n, not just r squared or r cubed. Another one would be like a weighted dot product, we can call it. Product. So we do u1, u2 through un, dotted with the v version, v1, v2 through vn, would be some, let's just put some various coefficients in front of each one of the products, u2, v2, etc. Lambda n, un, vn. So you can imagine this being useful in a case like, suppose you're trying to do some statistical analysis and you know that the second entry should have much more weight than the first entry. So you want to make lambda 2 bigger than lambda 1. So these do have real applications, and then let's do another wacky example. That would be like, take our vector space to be all polynomials, maybe, of degree up to 2. Alright. And then you could do, so let me fix the notation on the previous one. Alright, so with this you could do something like the inner product of a plus bx plus cx squared, and let's see here, let's come up with d plus ex plus fx squared. Maybe we want to just multiply the corresponding coefficients, ef. Right, so this should look a lot like a dot product because it essentially is. You might even want to call this the dot product on P2. And so any vector spaces that have the shape that looks like some r to the n do have inner product that looks like the dot product. And all of their possible inner products look like weighted dot products. Now I just want to take a moment that noise my dog is making is the noise she makes when she attacks her foot. So, enjoy it. It's a very funny thing she does. Alright. Let me give you just one more example. Let's take the vector space of continuous functions from 0 to 1. Okay, so every continuous function is integrable. So let's say the inner product of two functions in this space is the integral from 0 to 1 of the product of those functions. Alright. So let's take a moment to go back. Does this satisfy our property 1, which was our commutativity? Yes, well, because if you swap the order of f and g within your integral, you're still going to get the same thing. Alright. 2 asks distributivity. And yeah, that works too because this is a multiplication, so it works just like multiplication. 3, scaling. Yeah, okay. Right, if you put a scalar in here, you could put it over with the g, you could take it outside the integral. And lastly, integral is only 0, so the integral of f of x times f of x from 0 to 1. F times f is a positive function, and so the area underneath it is non-negative, good. Greater than or equal to 0, check. And it's only equal to 0 if there's no area to take, if f itself was just the 0 function. If and only if. Alright. So there's a goofy example. You're going to see that in the slides today. But I just wanted to talk a little bit about where our inner products come from, and it just comes from the generalization of the dot product and the desire for each of these theorems. Alright, excellent. That's all for this video. Have a good one. Bye-bye.